Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve a problem fresh off the Leetcode contest for today, maximum subarray min product. So this is a pretty hard problem even though it's categorized as medium, and I'm just going to tell you that this is a problem that can be solved with a monotonic increasing stack. Basically, we're going to use a stack data structure and it's always going to be in increasing order. And let me just tell you that if you've never heard of a monotonic increasing stack, basically you probably wouldn't have a good chance of being able to solve this problem on your own. I've actually heard of this type of problem before and I still wasn't able to recognize that this could be solved with a monotonic increasing stack, so don't feel too bad about yourself. So we're given a definition: a min product of an array is equal to the minimum value in that array multiplied by the sum of that array. So for example, the minimum value is 2 and the sum of the array is 10. So we're going to take 2 times 10, then that's going to be 20. And so in this case, we're actually given an entire array and we want to find what the maximum minimum product is of any of those subarrays of the given array. So basically we have to try this computation for every single subarray of the nums that we're given. And it might be a really large number, so we're going to have to mod it by this prime number that they give us. But this is just a minor detail we can worry about later. And they tell us a subarray is basically a continuous part of an array, such as this. So let's start out with the brute force approach. The brute force is actually big O of n squared. Let me tell you why. Let's just try every single subarray of this given input array. So we're going to start here. We're going to get the sum. It's going to be 1 so far, and the minimum number is 1, so we're just going to get 1 times 1. Then we're going to add these two numbers, right? The minimum number is still 1, but the sum is now going to be 3, so 3 times 1. And so on and so on. We're going to add this number, the sum is 6, minimum value is still 1, and then we're going to get the entire array. But so far, and we just did that in big O of n time, right? We were just starting at the beginning, iterating through the end. We did that in O of n time, but we didn't do every single subarray, right? We started over here. Now let's get every subarray starting at this value, right? So we'd have 2 is the minimum value so far. And then we add another value. 2 is still the minimum. The sum is now 6, right? And so on. And then we'd get through to the end of the list. Then we'd want to get all subarrays starting here. So we'd start here and then go to the end of the list and so on and so on. And then that would be big O n squared. That's not a bad solution, but it's possible that this can actually be done in big O of n time. And it's not actually going to be needing a sliding window. You might think, okay, a sliding window will work. We'll have a left pointer and a right pointer, but no, that's not going to work. And let me show you why. We're going to be needing a stack to solve this problem. So as I mentioned, we're going to be needing a monotonic increasing stack to be able to solve this problem in big O of n time. That's also going to take big O of n memory because we are using that stack data structure. But let me explain the logic. The main logic that we're going to follow is we want to consider if each value in the input array, like this 1 or this 2, was the minimum value of the subarray, and then we want to make that subarray as large as we possibly can, right? Considering if, let's say, 1 was the minimum value in the subarray, how large can we make the subarray if we expand outward? And that's pretty simple, right? And we want to do that for every single value. And once we've done that, and then we get the maximum of all possibilities, then we have our result, right? That makes sense so far. So let's start at the beginning of this input array and keep iterating towards the right. So first value we see is a 1 value, right? Let's consider if this 1 was the minimum value of the subarray. Let's see how large we can make that subarray. So we visited the 1, now let's get to the next value, it's a 2. So notice that so far our input array is in increasing order, right? That's pretty important. But why is that important? Because we're considering if 1 was the minimum value in the subarray. We added another value and that value is greater. So far our condition is true, right? We want to see how large we can make the subarray. So for considering this 1 value, so far we have a subarray, right, of width 2, but we don't care so much about the width of the subarray in this problem. We care about the total sum of the subarray, right? So let's say our input array was still in increasing order. Let's say we had a 3 at the next position. And even so, that 3 could actually be a 2, and we would still count that as increasing order because we're counting equal values as still considered as basically increasing order, right? And for this 1 value, we can continue to expand, right? Why is that? Because 1 is still the minimum value of this subarray. But what about 2? Can we simultaneously consider this as the minimum value of the subarray as well? Well, technically, we can't include this as the subarray. If this were the minimum value, we can't consider this 1 as part of the subarray, but we can say that, okay, from where this 2 started, the start value of the 2, so far of all the values that we added, it is the minimum of the subarray. So this is very important. For every value, we're considering its start position as where the subarray for that value starts. And so let's say this was the end of the input array. How would then we compute what the possible result was? Because so far, this is our stack, and it technically is in increasing order. Well, then in that case, we would basically, at the end, we'd once again iterate through every single value of our stack. This is what we would say. We would say, okay, for this 1, it started at index 0 and it went all the way until the end of the input array, right? This was the largest subarray. This value happened to be the minimum. So we're going to get the sum of that subarray, which is 5, multiply it by the value 1, and we're going to get 5 as a possible result. We're also going to say, okay, for this value, well, it didn't start at index 0, it started at index 1, but it still ended up going until the end of the array because our stack was in increasing order. So we're going to say that this was the subarray where this value happened to be the minimum, and the sum of that subarray happened to be 4, and the minimum value happened to be 2. So 4 times 2 is going to be 8, right? So we actually found a value. Before we had 5. Now our maximum is going to be 8. And technically we do it for one more value in this case, but we'll see that this is going to be smaller, right? The minimum value. This starts over here. So the subarray happens to be this, and the sum of that subarray happens to be 2. The minimum value is also 2. So we're going to get 2 times 2. That's going to be 4. It's not less than 8. So when our input array is in increasing order, this is kind of how we can handle it, but that's not always going to be the case. What happens if our input array is in decreasing order? Let's take a look at that case. And so remember what we're doing for each value, we're considering if it was the minimum of that subarray. So we're going to look at the first value 2. We're going to consider if 2 was the minimum of the subarray, right? And we know that this 2, the start of that subarray is going to be over here, right? Because that's where we first encounter this 2. So now let's look at the next value, 1. Hold on a minute. We were assuming that this 2 was the minimum of the subarray, but we now have a new minimum. We have a 1 value in the subarray. So what does that tell us? That tells us that if we were considering this as a part of a subarray, that subarray has to stop before we get to the 1. So what we're going to do in this case, since our stack is not in increasing order, we need to make it in increasing order. So we're going to pop this value from our stack. We're going to pop the 2 from our stack. And when we pop that 2, we're also going to see that, okay, that the start value was at index 0, right? And we got to index 1 over here, right? This is index 1. So basically what we're saying here is for this 2 value, which happened to be the minimum of that subarray, it went all the way from index 0 up until index 1, but not including index 1, right? So really what we're doing here is once we pop this 2, we want to know what's the max subarray that it was a part of, and then we want to compute what the minimum product of that subarray was. So what we're going to do is then in that case, what we're going to say is we're going to get the sum of the input array from index 0 up until index 1, but not including index 1. And we're going to multiply that sum by 2. Because we already, for this 2 value, we found the maximum subarray that it was a part of, and now we don't have to consider it anymore. That's why we're removing it from our stack. Okay, so we ended up visiting this 1 at index 1, and now we notice we have no more values, right? For this 2, we already considered if it was the minimum of a subarray, and we got that subarray and we computed that total, right? But now we have this 1, right? And since there's no more values left, let's consider if this value is the minimum of a subarray. How large would that subarray be? Well, we notice we added this 1 at index 1. So can we just say, okay, this is the maximum subarray? Technically not, because see, we removed a value from our stack, and that value was actually larger than this 1. So when we want to consider the max subarray that this 1 is a part of, we're going to start extending it to the left as we pop elements, right? Since we popped this 1, we're not going to consider this as starting at index 1. We're considering it as starting at index 0, right? And that makes sense, right? Because if you take a look at this subarray 2 and 1, 1 is the minimum value of this entire array. So it makes sense that we would do that. And what is the total that we're going to compute? Well, when you take the sum of this subarray, we get 2 plus 1, which is 3, multiplied by the minimum value of the subarray, which is 1, and we get 3 times 1, which is going to be 3. And that's not going to be the answer. The answer is going to be 4 that we computed earlier. But this is just a little bit of the intuition behind the problem. Now let me actually show you what it would look like when we run through an example case like this, and let me show you what exactly we're going to be doing with our stack data structure. So this is the problem setup. I have an input array and I'm going to have a stack. But before I get into that, let me just explain very quickly. We know that for an arbitrary subarray, like maybe this one, we're going to need to be able to compute the total sum of that subarray, and we're going to need to be able to compute it quickly, right? Because we're going to be potentially doing that a lot. So there's a way to do that in O of 1 time. What we're going to do is we're going to pre-compute the sum of every prefix. So this is one prefix of the input array. We're going to compute that sum. That's 1. We're going to pre-compute the prefix like this, which is sum 3. We're going to pre-compute the prefix of this, which is sum 6. How is that going to help us potentially get the sum of an arbitrary subarray like this? Well, we can take the prefix this that we computed and subtract from it this prefix, right? So that's just a little bit of the intuition of why we're using prefixes. We'll get more into when I actually write out the code of this problem, but for now, we're just going to take that for granted that we can compute a sum of a subarray in O of 1 time. So we're just going to be going from left to right in our input array. So we're going to look at the first value. It's 1. It starts at index 0. So what are we going to do? We're going to go ahead and just add that to our stack. So we're going to say, okay, what value are we adding to the stack? We're adding 1. Okay, what was the start position of that value? It was at index 0. Great. And as you can see, our stack is so far in increasing order. So we're just going to go ahead and continue to add values. Remember, an increasing stack is what we want. Since our input array is in increasing order, we're just going to go ahead and add this value to our stack as well. So we're adding the value 2. It started at index 1. And once again, our stack is in increasing order. So we're going to take 3, add it to our input array. It started at index 2. So let's do that. But hey, now we finally got to a value that's in decreasing order. So what are we going to do? We want our stack to always be in increasing order. So what are we going to do? While the top of the stack, while the top value in the stack over here is greater than the value we're looking at right now, we're going to start popping from our stack. So we're going to pop 3 from our stack. And once we pop it from our stack, we're going to compute, since we know what's the maximum subarray it could possibly be a part of. We know that we could not extend it any more to the right, because if we did, we'd find a new minimum value 2. And we know that it could not have been extended to the left because the stack was our input array was in increasing order, right? So we would definitely not be able to make the subarray larger to the left. So this is our entire subarray, right? So we're going to compute the sum of the subarray in O of 1 time. It's just 3, right? The minimum value of that subarray is basically the value that we just popped, which is also 3. So 3 times 3 is going to be 9, right? So far, I'm just going to put 9 over here as our maximum so far. Now, once again, we're going to look at our stack and see, is the top value in our stack greater than the value that we're looking at right now? It's not. It's equal, so that's perfectly fine. If it's equal, it can remain there. But so now we're finally allowed to go ahead and put this value in our stack. So we're going to add 2 to the stack, and this value started at index 3. So am I going to add 3 as the start value to this stack? Well, remember what we're trying to do here, right? If this value was the minimum, we want to know what's the biggest subarray it could possibly be a part of if it was the minimum. And technically it can be extended to the left, right? That's why we popped this value. That's another reason why we popped this value, because it tells us how far back can we take. We know we're going to, as we iterate through the array, we're going to be extending this to the right if we're allowed to, but we can also extend it to the left as we pop elements from the stack that we just did. So since the last element we popped started at index 2, right? That's what, when we popped it, that's what we got, the index 2. So what we're going to say for this value is it started at index 2, not at index 3. And technically, you might think that, okay, well, can't this actually be extended even one further over here, right? Because this subarray also has a minimum value of 2. And yes, you're technically correct, but that's actually not necessary because that is actually already stored in our input array. We see 2, 1 is here. This 2, 1 tells us that this 2 is the minimum value of a subarray starting at index 1. That's what the start value of the stack tells us, right? It's at index 1. It started there. And so far, since that value is still in our stack, what that tells us is so far this 2 was the minimum value, and we were able to extend it all the way to the end of the input array. So now you can see that we were able to actually iterate through every single value in the input array, but notice how our stack is still not empty. We only popped one value from our stack. When we popped a value from our stack, basically that told us that the subarray was complete. If 3 is the minimum value, it started here, it ended here, and that's what the subarray it was a part of. That's what we're going to compute for our result. But since these 3 values are still in our stack, and we know the start values of all of them, for 1, it starts at index 0. For 2, it starts at index 1. But what's the end value for these? Technically, since we were able to get to the entire end of the input array, the end is just going to be the end of the input array. So what I'm saying is, if we want to know for this 1 value, if it was the minimum of the subarray, how big is that subarray? Well, it's going to be just the entire input array, right? That makes sense. Take a look. 1 is the minimum value of the entire subarray. That does make sense. What about 2? Well, we know 2 starts at index 1, so that's going to be the start of that subarray. How far did it go? It went until the end. So when you look at this, that does make sense. 2 is the minimum value of this subarray. So since all of them went until the end of the subarray, let's start computing. So let's look at the first value in our stack. It's 1 and the start value was 0. So we're going to get the sum of the entire input array. That's going to be 8. And the minimum value of the subarray was just the value that we popped, 1. 1 times 8 is 8, and that's not larger than our current maximum. We're done with 1. Let's get to the next value in our stack. So we pop this. Now let's look at this next value. Okay, it starts at index 1. The value is 2. So let's get the sum of this subarray. We know we can do that in O of 1 time. And it happens to be 2 plus 3 plus 2, that's 7, multiplied by the value, the minimum value of the subarray, we know that's 2. 2 times 4 is going to be 14. So far, our new maximum is actually going to be 14. So cross out the 9, put a 14. And we can see we have a single value left in our stack. So we're going to pop 2, 2. The first 2 tells us this starts at index 2, and the minimum value is also 2. So 2 is the minimum value. Let's get the sum of this subarray. It's going to be 2 plus 3. That's 5. The minimum value is going to be 2. So multiply this by 2. That's going to end up being 10. It's not larger than our maximum. But let me actually show you the code the way that I like to write it. It's going to be O of n time, O of n space. Let's get into it. So we're going to have a single variable for our result. Remember, we're looking for the maximum that we can possibly get. We are going to have a stack, which is going to be in monotonic increasing order. And we're also going to have a prefix array where we compute every single prefix of the input array, just so we can compute the sums of any arbitrary subarray in O of 1 time. So I'm going to just go through every single n in the input array. So I'm just going to be appending every prefix to this. So we're going to get the previous prefix, basically the last value that was added to our prefix array. And to that, we're going to add the most recent value n that we're iterating through. Now for the actual algorithm, let's go through every value in nums. So in, I'm going to use enumerate so we can get the index and the value in nums at the same time. And I'm going to have a single variable for the new start. And it's going to initially be set to I. Now we're going to check if our stack is non-empty and the top value in our stack, which we can get at the -1 index. And remember, we're adding a pair of values to this stack. At 0 index, we're going to have the index that we add. At index 1, we're going to add the actual value that we added to the stack. And if this value happens to be greater than the value that we're looking at right now, which is n, that's when we're going to end up popping from our stack because we want our stack to be in monotonic increasing order. And when we pop from the stack, we're going to be getting a pair of values from it, basically the start index and the value that were added to that stack. And since this value is now being popped, what we're saying is we just determined what the max subarray it could possibly have been a part of. So now we're going to end up computing what the minimum product of it would have been. So first we're going to get the total of the subarray that it was a part of. So we know prefix of I is basically the sum of every value up until this value was popped. And from that, we're going to subtract prefix of start. We're just getting the sum of the subarray that this value is a part of. So basically the sum of the subarray from the start index all the way up until the I index that we just iterated to. So now that we have this total, we can potentially update our result. We're going to update the result to the max of what it already currently is, or update it to the minimum product that we're going to compute right now, basically the value multiplied by the total sum of the subarray. And last but not least, what we're going to do, since we popped a value, this n value, we're going to ultimately be adding it to our stack, right? Ultimately, we're going to say stack.append this value n, right? Because we're saying I is the start value of this n value, but we see that we just popped a value from our stack. So what we're actually going to say is the new start value can be pushed back by 1. So what we're going to do is say new start ends up being equal to the start value of the value that we just popped from our stack. My words probably are a little confusing, so you can refer back to the visual explanation that I drew a second ago. So in reality, we're not actually going to be adding I every single time. We are initializing new start to I, but if we end up updating it, we're going to be adding new start to this stack as the start value of this n. So by the end of this loop, we will have added every single value to the stack, but we won't necessarily have popped every value from the stack. So we're going to go through every remaining value in the stack. We're going to get the start index and the value of every single pair in our stack currently. And again, just like we did up above, we want to be able to compute the total of the subarray that this value was a part of, right? The biggest subarray that it was a part of. Well, we clearly have the start value of the subarray, but what's the end value of the subarray? Up here, the end value was the index I, but in this case, we know we went up until the end of the entire input array. So the end value, the end index in this case is going to be the length of the input array. So we're going to say prefix up until the end of the entire input array length nums subtracted by the prefix up until the start value of this value that we popped, the start index that we popped. Once we have that total, we can again potentially update our result just like we did up above. So result is going to be equal to max of itself and the max of the value that we popped multiplied by the total of the subarray that it was a part of. So then finally, after we've done this, we've gone through every remaining value in our stack, then we can finally return the result. But remember, they wanted us to mod it by 10 to the power of 9 plus 7. So this was a real doozy of a problem trying to get it from n squared to actually being a linear solution, but we finally did it. There's a lot of different ways to write this code, but I think, at least in my opinion, this is the most intuitive by adding a pair of values to our stack so we can actually maintain the start index of every value that we added. And of course, we have to compute the prefixes. And I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.